Now, along with arithmetic sequences, there exists another set of sequences which don't have a common difference between their terms. Okay, that as you look at their terms, we notice that the differences between any two pairs of consecutive numbers doesn't stay constant. If that's the case, if we have the difference changing between any two consecutive terms in a sequence, then we describe that sequence as being non-linear. Okay, so therefore I suppose you can also say we describe arithmetic sequences as being linear sequences because they produce the same difference between any two pairs of consecutive terms along that sequence. But when that's not the case, when you take a sequence and you take any two pairs of consecutive numbers and you look at the differences between them and they don't appear to be common, then we're into the non-linear section of sequences. And there are only two types of non-linear sequences we want to look at in this section. They are the quadratics and they are the cubics. Now, we already know what quadratic and cubic equations do. We've worked them in terms of functions, we've looked at them, we know how to solve them and so on, but we're going to apply them in terms of sequences. How can we recognize a sequence to be a quadratic sequence or a sequence of terms that's being generated by a quadratic function? Okay, or how do we recognize a sequence of numbers that's being generated by a cubic function? And the answer lies in where the difference comes out as a constant. Now, what do I mean by that? Well, go back to your arithmetic sequence. When you took your arithmetic sequence and you looked at the differences between all the consecutive numbers, it was the same. Say, for example, we get a set of numbers in a sequence where the first level difference is not the same. What we then do is we look at the difference between the differences and see, does that come out as a constant on the second level? And if it does, then it's a quadratic function that has generated those terms. If that constant in the differences doesn't fall out until the third level, then we know that these numbers in this sequence are being generated by a cubic function, and we would call that a cubic sequence. But we'll take a couple of examples now in a moment. A non-linear sequence, as I've already said, is one where the difference changes between each pair of consecutive terms. So take a look at this one here: 3, 6, 10, 15 and 21. Take the difference between 3 and 6, 3. 6 and 10, 4. 10 and 15, 5. 15 and 21, 6. Immediately, not an arithmetic sequence. If it was an arithmetic sequence, those differences would be constant. They'd be common, okay? So what I now do is I look at the differences between the differences. So 3 and 4 is 1, 4 and 5 is 1, 5 and 6 is 1. So what's happened is the constant has arrived, the constant has been found, but it seems to exist on the second level difference. Okay, so this is the first level of differences, and this is the second level of differences. When the constant appears, whatever level the constant appears on, that is the same as what we would say is the order of the function that is generating the terms. And the order simply means whether it has the highest power 1 or 2 or 3, i.e. whether it's linear or quadratic or cubic and so on. Okay, now let's just take a look at what the slides say. So there you go, there's your differences. 3 and 6 is a difference of 3. 6 and 10 difference of 4, 10 and 15, and 15 and 21. So the first level difference, or the first differences, are not common, not constant. Therefore, it is not arithmetic, not linear. Let's look at the differences on the second level. The difference between 3 and 4 is 1, 4 and 5 is 1, 5 and 6 is 1. And because the second difference is a constant, we now know that this is definitely a quadratic sequence. Okay, so the original sequence was quadratic. The first differences, as we've already said, are 3, 4, 5 and 6 and are not common. But the second difference, or the difference on the second level, is a constant. And because it's constant, we refer to that as being the second difference. And the second difference means that if it's constant, you're dealing with a quadratic sequence. Quadratic sequences have a constant difference on the second level of their differences. The nth term of a quadratic sequence is of the form t of n equals an squared plus bn plus c. No surprise there. Every single quadratic equation that we've worked with has a square term, it has a variable term, and it has a constant. Okay? So that's just a general form of a quadratic equation. an squared plus bn plus c. Think, for example, 3x squared plus 6x plus 9. Okay, so that's nothing more than a general form. But what I do want you to notice is this, that in the general form, or the general term formula of a quadratic sequence, there are three variables, a, b, and c, that we will be asked to find. Okay, now there's a connection for one of them, and that connection is a. And here's what we know. If you're given a sequence and you work out that the first level differences are not constant, then it's not linear. If you go to the second level differences and they are constant, then you're dealing with quadratic. But the second level difference, the value of the second level difference, is equal to 2 times the coefficient of the squared term. In other words, the second difference is equal to 2a. So it is a relatively easy thing to find a once we're given a few terms of the original sequence and we're told that it is quadratic. Okay, so here's an example. Show that the sequence 1, 6, 15, 28, 45 is quadratic. Now, if we're told to show that it is quadratic, what does that mean? First of all, that the second difference is constant. Okay, so let's do that. 1 and 6, 5. The difference between 6 and 15, 9. 15 and 28, 13. 28 and 45 is 17. Okay, so the first level difference, not constant, therefore it is not arithmetic. Let's go to the second level. The difference between 5 and 9, 4. 9 and 13, 4. 13 and 17, 4. So therefore there is a constant second difference. And the constant second difference is equal to 4. So we write that down. Second difference is equal to 4. So what I've done is I have proved that this particular sequence is quadratic because the common difference or the constant difference doesn't fall out until the second level of differences. Okay. In any quadratic sequence defined by an squared plus bn plus c, the second difference is set to 2a. So in other words, when you work out the value of your second difference, the second difference is always twice the leading coefficient. This then allows us to find the coefficient of the quadratic if we know the second difference. So let's take a look at this question here. Find the value of a, which is the leading coefficient, the coefficient of n squared, in the quadratic sequence t of n equals an squared. Also find the value of the 10th term, that's t of 10. So we want to work out that one. The first 5 terms of the sequence are good. So that's what we need in order to work out, first of all, is it quadratic? Now we're told it is in the quadratic. So we're told it is. So it should have a, if you think of it, a second difference that's constant. So let's go to the first differences. 3 and 12, 9. 12 and 27 is 15. 27 and 48, that's going to give me 21. And 48 and 75 is 27, I think, yeah. Okay, second level, that is 9 to 50, that's 6. 15 to 20, yeah, that's 6. And then 21 to 27, 6. 3 6s. I hope you're not watching Damien on Fox Television, because he has 3 6s on his head. But that's not the same 3 6s, they're different. This is 666 as a common second difference. Okay, we're proving something is quadratic, so stay away from the old mysticism there. So 666, what does that mean? That means that the second difference is 6. Now, the second difference is also twice the leading coefficient. So if 6 is equal to twice the leading coefficient, well then 3 must be the leading coefficient. And where do I put that? Back into the formula where a is. So therefore t of n now becomes 3 times n squared. Good. And how does that help me? Well, look at what they asked me to do. Also find the value of the 10th term. I can't find t10 until I know t of n. And if t of n is 3n squared, then t of 10 is nothing more than 3 times 10 squared, which works out as 300. So that's how you tackle that question. Quite easy, but just keep in mind for a quadratic sequence, it's the second difference we're looking for, okay? And the second difference will be a constant, but the value of that constant will also be twice the coefficient of the n squared term, or put another way, twice the value of the leading coefficient. Now this is one that involves finding the values of a, b and c, okay? And I just want to point out how much mathematical knowledge we have to allow us to do this. We should be able to see into this straight away. T of n equals an squared plus bn plus c is a quadratic sequence. No surprise there, because a quadratic sequence has the same form as a quadratic expression, okay? Just keep that in mind. The first 5 terms of the sequence are 12, 16, 23, 33 and 46. Now, because I know it's a quadratic sequence, I immediately look to see what is the second difference. 12 to 16, 4. 16 to 23, 16 to 23, what's that? 6, 4, 7. 23 to 33 is 10. And then 33 to 46 is 13. Okay, so we don't expect a constant to follow it in the first level. If we did, it'd be an arithmetic sequence. It's not. It's quadratic. So now I expect to get my constant falling out. 3, 3, and 3. That's Damien's little brother. 3, 3, 3. Now, if 3, 3, 3 is the second difference, and I also know that the second difference is equal to 2a, well then what do I get? 2a is equal to 3, a equals 3 over 2. So I have immediately discovered what a is. So I go back to my T of n formula, and I substitute 3 over 2 in for a. So you get 3 over 2 n squared plus bn plus c. So now we've got a. Look at part 1. Find the values of a, b and c. I have discovered a. I know a. So find b and c. Go back to what I told you in the first 3 chapters of book 1. If you are being asked to work out 2 variables, you can only do that with a pair of simultaneous equations. So I need to take this formula here, and I need to get it to generate 2 equations that I can solve simultaneously. So therefore, if I want to find b and c, I have to know the value of n, and I also have to know the value of a given term. Go back to the sequence. 12 is the first term. 16 is the second term. See that? So there they are. Just use those 2. T1 is 12. So down here, here's what I'm going to put. T1 is equal to 12, which is also equal, because the n is now changed for 1, I'm going to put n in here. So it becomes 3 over 2 times 1 squared plus b times 1 plus c. So I get 12 equals 3 over 2 plus b plus c. There's my first equation. Now you can subtract 3 over 2 from both sides, and you'll end up getting 10.5 is equal to b plus c. So there's equation 1. And what do I do next? Do the same thing with T2. What's T2 equal to? T2 is equal to 16, which is also equal to this formula with 2 put in for n. So 3 over 2, 2 squared, plus b times 2 plus c. So 16 equals 2 squared is 4, 4 divided by 2 is 2, and 2 times 3, 6, plus 2b plus c. Now subtract 6 from both sides, 10 equals 2b plus c. And there's my second equation. Okay, now how do I solve b and c in both of these? The answer is you take them together as a pair of simultaneous equations. 2b plus c equals 10, and b plus c equals 10.5. So all I've got to do now is cancel the c's. So I'm going to change all the signs down here. Let me just do that in a different color. So I'm going to change that to minus, to minus, and to minus. And that's going to allow me, it's going to allow me to cancel the c's. 2b minus b is b, equals 10 minus 10.5 minus a half. So there's b. And the only thing I've got to do now is to bring b back to either one of these 2 equations. It doesn't matter. Let's bring it back over here. And let's put it in. 10.5 equals minus 0.5 plus c. So therefore, add 0.5 to both sides. 11 equals c. So I now have a. Where's a? Up here. Which is the coefficient of the leading coefficient, the coefficient of the n squared term. B minus 0.5, and c is 11. So that means that I can now write out my T of n formula fully as T of n equals 3 over 2n squared minus 0.5n plus 11. In other words, t of n equals a n squared plus b times n plus c, where a is 3 over 2, b is minus 0.5, and c is 11. What does it say at the end? Hence, so using what you've done, find t30. Well, that's easy, because that's where I change n for 30. 3 over 2 times 30 squared minus 0.5 times 30 plus 11. So what does that come out as? 30 squared is 900. 900 divided by 2 is 450. And 450 multiplied by 3 comes out as 1350. Minus 15, because a half of 30 is 50. So minus 15 plus 11. Now look, plus 11 minus 15, that's minus 4. So that's 1, 3, 4, 6. And that is t of 30. Okay, so what are we falling back on? We're falling back on the earliest algebraic things we learned, probably back even in second year. Simultaneous equations, when you're asked to work out the value of two variables. The way in which we do that, always, two variables, you need two equations in those variables, i.e. a pair of simultaneous equations. What about cubic sequences? Now, look, if you have an arithmetic, and by the way, arithmetic is linear. Okay, and the reason why it's linear is because the first level difference is constant. All right, how do they generate them? A plus n minus 1 times d. What about a quadratic? Well, the quadratic formula is exactly the same as the quadratic expression, a n squared plus b n plus c. So therefore the cubic one will be a n cubed plus b n squared plus c n plus d. Okay, now they won't ask you any complicated algebra with cubics. The only thing they will do is they will throw you a sequence and they'll ask you, prove that this is cubic. How do I do that? If linears have a first level constant difference and quadratics have a second level constant difference, well then cubics will have a third level common difference or constant difference. Okay, so you basically take the level on which the constant difference falls out as being the order of the sequence. So if it's a first level, then it's linear. If it's a second level difference, then it is a quadratic. If it's a third level difference, then it is a cubic sequence. And if that's what I'm just saying here, a cubic sequence has the general term formula a n cubed plus b n squared plus c n plus d. For a cubic sequence, the third difference is a constant. So here's an example, and this is probably all they're ever going to ask you about cubic sequences, so don't worry about them. Show that the sequence 2, 10, 30, 68, 100, 22 is cubic. Now, what does cubic mean? Cubic means of degree 3. Degree 3 will give you a constant on the third level, or to give you a third difference. So let's see the first difference. 8. Here, 20. Here, 38. Here, I'm going to have to use my calculator for this. I'm too old to be doing this kind of thing. 130 minus 68, that is 62. And then 130 and 222, and that comes out as 92. Okay, that's my first level, not constant, therefore not arithmetic. Let's go to the second level. 8 and 20, 12. This one here, 18. This one here, 24. And this one here, 30. So the second level difference isn't constant. Let's go to the third level. 12 and 18, difference is 6. 18, 24, 6. 24, 30, 6. Whoops, here we go again. 6, 6, 6. Third level difference, meaning what? It is a cubic sequence. If the difference doesn't appear to be constant to the third level, and that's what we're on the third level, then it is a cubic sequence. Okay, if the common difference falls out in the first level, arithmetic, linear. If it falls out in the second level, quadratic. If it falls out in the third level, it's cubic. Okay. I think I have this already printed out here for you, as far as I know. No. So remember, a linear sequence has a first difference being a constant, okay? And it also has the general term formula t of n equals a plus n minus 1 times d. A quadratic sequence has the second difference as a constant on the second level, okay? And it has t of n equals a n squared plus b n plus c, which is the same kind of structure as a normal, what we would call a quadratic expression. And then the cubic sequence has a third difference. That means that the difference is constant on the third level of differences, and it has a general term formula of an cubed plus bn squared plus cn plus d. Okay, so keep that in mind. Now, let's take this look at this question here before I give you some work to do yourselves. This is on page 213, question 7. The pattern of dots as shown below represent the first 3 star numbers. Okay. Part 1. What are the first 3 star numbers? Well, let's take a look. So you notice there's a square at the middle of each one. So that's a 2 by 2. So that's 4. And then there are 1, 2, 3. There's 4 dots there. So that's 8. So that's a 4 plus 4. Okay. Here I have 3 3s, which is 9. And then I have, so they're done. So I've done those. That's 9. And then I've got 4 triangles of 3 each. 4 3, that's 12. So that's 21. And then here I've got a 4 by 4 square in the middle, so that's 16. And then I've got 4 triangles of 1, 2, 3, 4, 5 of 6 each, so that gives me 40. So the first 3 star numbers are 8, 21 and 40. Now, my advice would be, don't work with sequences unless you have at least the first 5 terms, because we're not too sure whether this is linear. Well, it's definitely not linear, because 8 to 21, 21 to 40 don't have the same common difference, but we don't have enough information to go on to a second or a third level. So what I'm going to do is I'm going to try and find out, can I generate the next 2 terms? Okay, if this is a 2 by 2, see that? There's a 2 by 2, that's in here. So 2, that's 4, that's those, and then 5, 6, 7, 8. Right, what do we have? Let's see if we can work out a rule. I want to generate the next 2 terms for this one. So let's take the first one. It's a 2 by 2 plus 4 singles. Okay. The next one is a 3 by 3 at the center plus 4 triangles containing 3 dots each. Okay. The next one is a 4 by 4 and 4 triangles containing 1, 2, 3, 4, 5, 6 each. Now, what would the next one be? It'd be a 5 by 5, wouldn't it? With 4 triangles containing 4, 3, 2 and 1, which would be 10. The next one then would have a 6 by 6 square in the middle and 4 triangles of 15 dots in them. Okay, so I'm just building up the pattern. Where are we here? 2 2s. Actually, I better just take that off and let you see the original diagram. There. Okay, so we've got 2 by 2 in the middle plus 4 singles. So 2 by 2 plus 4 ones. Okay, here 3 by 3 plus 4 3s. Next one, 4 by 4 and then 4 7s. See that? 4 6s. And then you write those down and look at the pattern. 2 by 2 plus 4 1s. 3 by 3 plus 4 3s. 4 by... So now I work out what the next 2 terms are. So let's do 5 5s. So that's going to be 25. And 25 and 40 is 65. Next one, 6 6s are 36. And 36 and 60 is 96. So now I've got 5 terms of this thing. So what do I know? I know that 8 and 21, let's have a look and see if we can get the differences now between all these. And because of the fact that we're dealing with a sequence that we're not too sure whether it's quadratic or cubic, we're going to have to look at all the differences here and see where the common difference falls out. 8 to 21, what's that? That's 13. Okay. 21 to 40, that's 19. 40 to 65, that's 25. And then 65 to 96 is 31. Okay, so that's my first level, so it is not there. Let's go to the next level. 13 to 19 has a difference of 6. 19 to 25 difference of 6. 20, so it has a second difference equal to 6. And don't forget what I told you. Now that I know it's quadratic, what does that mean? That means that 6 is also twice the leading coefficient. So immediately from that, 3 is equal to a. And because it's quadratic, t of n equals a n squared plus b n plus c is the general term formula. Okay, so I've got to remember that. Now that I've discovered it's quadratic, I write down what the general term formula of a quadratic is, and I also remember that the second difference is equal to 2 times the leading coefficient, 2a. So I divide the second difference by 2 to work out what the leading coefficient is, and it's 3. So what does that tell me? That tells me T of n equals 3 times n squared plus B of n plus C. Now here's the thing. I've got to work out the value of B and C. So therefore, I need to get two equations in B and C. And the only place that I'm going to get them from are from the two terms. Let's take the first two terms because they're the smallest numbers to deal with. So let's deal with them. T of 1 is equal to 8. We all agree with that. The first term is equal to 8. But then n has become 1. So I can also do that in here. 3 times 1 squared plus b times 1 plus c. So therefore 8 is equal to 3 plus b plus c. What does that give me? That gives me 5 equals b plus c. So there's my first equation. Okay, let's take the next one. T2 is equal to 21, which also means that if I put 2 into this general form here, I'll get 3 times 2 squared plus b times 2 plus c. And that's going to give me 4 3's 12 plus 2b plus c is equal to 21. So subtract 12 from both sides. 9 equals 2b plus c. And there's my second equation. So all I've got to do now is take equation 1 and equation 2 together. And we'll write down 9 equals 2b plus c. Underneath that, 5 equals b plus c. We're then going to change the signs of the bottom line, like so we can get the c's to cancel. The c's cancel, and I'm left with 9 minus 5 is 4, is equal to 2b minus b is b, and there's b. And the last thing I do then is I go back to here, back to equation 1. If 4 is b and 5 is equal to b plus c, well then obviously, look at that, 5 equals b plus c. So 5 equals 4 plus b, so therefore b is equal to 1. So now I've got my a, there it is. I've got my b there, and I've got my c. I should say that's c, isn't it? Yeah, that shouldn't be b. That should be c. So c and c equals 1. So now, what can I do? Now I can go back and write out my T of n formula fully. T of n equals an squared, so that's 3n squared, plus b of n, so that's plus 4 times n, plus c, which is plus 1. And that is the T of n formula with the values of a, b, and c discovered. And then it says down here in part 3, using your formula from part 2, find the 50th star. So you're going to use T of n, and you're going to write out T of 50. So T of 50 is 3 times 50 squared, plus 4 times 50, plus 1. Now get your calculator to do that. So 50 squared, whoops, 50 squared multiplied by 3, and then we add on 450, we add on 200, and we add on 1. And the answer is 7,701. So that's it. So the 50th star number is 7,701. Okay, so that's just using the simultaneous equations. I just wanted to do that with you to show you how to do the simultaneous equations when they ask you for the T of n in a quadratic sequence. In a quadratic sequence, T of n has the same formula as a quadratic expression, an squared plus bn plus c. Okay, so keep that in mind. A will be nothing more than half the second difference. Then B and C are discovered by using a pair of simultaneous equations in B and C by using any of the two terms that come from your sequence and working out the values of B and C as we did when we started doing simultaneous equations back in second year. Okay. Now, I'm going to let you pause on this, so very short today, but again, practice makes perfect. So page 213, page 214, and the questions that are labelled there. And again, if you're in the middle of them and you need a bit of help, just send me an email and I'll get you back to solutions as quick as I can.